Hello everyone and welcome back to this series of videos on the Solow growth model. Specifically here, we are going to continue looking at aggregate equations and focus on how to derive the capital accumulation equation, which we are going to find out is going to become very, very useful. It's going to be kind of the key on everything, of everything that we're going to say afterwards. To begin with, let's start by defining the dynamic evolution of capital stock, as we see written here. Specifically, what do we mean by dynamic evolution of capital stock? We mean that we are going to find a way to define how capital tomorrow, so this kt plus 1, is determined. Specifically, this is going to be determined by 1 minus the depreciation rate multiplied by capital today plus investment. So what does this mean? We are basically balancing out new capital that is represented by investment in this case, and we've defined investment in our previous video, and old capital here. What we mean by old capital, I like to call it old capital. It's not really an economic definition, but we're basically taking whatever capital we had the previous period with respect to which we are kind of working, and we're going to see whatever is left after depreciation takes place. Summing these two up, we obtain the new capital stock. I would like to make a little note on how depreciation of old capital works. Specifically here, I set up 3 periods, so t plus 1, and t plus 2. So we're looking 2 periods ahead. Let's say we have 4 machines in our capital stock today. This is basically our KT. And we know that we have a depreciation rate of 0.5, which means that half of the machines every period break down. So basically, in the first period, we're going to have 2 machines that unfortunately, due to being too used, due to overuse, are going to break down. Hence, in the next period, we are only going to remain with 2 machines. So here we have our depreciation rate that works and leaves us with 2 machines. Hence, in period t plus 1, we are left with 1 minus delta, so 1 minus 0.5, which in our case is still 0.5 machines. But of course, we could assign any value to the depreciation rate. We could assign 0.2, and in the next period, we would be left with 0.8 machines, of course. And then, again, this depreciation takes place because it's a constant rate. We said it's exogenous. It's determined outside of the model. It's a parameter just given to us. And of course, in t plus 2, we're only going to be left with 1 machine. So again, this is how depreciation of old capital works. We said that capital accumulates according to this balancing between old capital and new investment made. But now, if we really want to fully define the aggregate way of, let's say, explaining a capital accumulation, we have to recall what investment is here. What is investment? We said that it's a fixed proportion of output. Why it's a fixed proportion for output? Again, because we have no international links, we have savings rate that are exogenous, and we say that since there are no international links into our model, we know that this is going to be equal to savings, but again, the savings rate is going to be exogenous. Hence, since investment is a fixed proportion of output, output is determined by the production function. Let's now look at a bit of plugging in using also our other equations. So we know that investment is defined as the savings rate times output. But again, we can make a further step and define output, as we've already done previously as well, by total factor productivity times the production function. Hence, we can now finally derive that our capital is going to accumulate according to the depreciation of all capital stock. So this remains like this, plus the saving rate that multiplies output defined by our production function. So yes, this in aggregate terms is our capital accumulation equation, and it's going to become very, very, very useful. Especially here we have a little spoiler alert for future videos where I would like to say in advance that capital accumulation will in fact be the main driver of growth in the Solow growth model. And we're going to see soon why this is the case.